Hello, CI 431. Welcome to our online class, and for this Monday, taking place of our usual class meeting. So before we get started, a couple quick things. Number one, I gave you a note sheet in class that you'll be using to kind of fill out as we progress through these slides. And when you come to class on Wednesday, that will be your kind of proof of attendance and keeping up with the syllabus expectations. So bring that with. You can print it on Moodle if you have lost it. Second thing is later in the slides, I'm going to do a little activity with you where it's going to be really helpful if you have 20 items. It could be 20 pennies, 20 paper clips, 20 Cheerios, 20 something. So right now, if you want to pause the video and go find 20 of something, they'll be helpful later in the presentation. And I guess a third thing is just the notion of an online presentation like this. Please use the pause button. When you need to pause to write in your notes, definitely pause. There's been some times too I ask you to pause so that you can try something on your own. Make sure you pause it and try it and then play the video and I'll give the answers. So just think about just trying to get the most out of your learning opportunity here. And I will see you Wednesday as regularly scheduled. So let's jump in. So this presentation is about Chapter 8, which is called The Meaning of the Operations. This presentation is not about how to compute with multi-digit numbers, not about mastering basic facts. Those will come later. This is really about starting the stage with thinking about the different meanings of the four operations. What are different ways of seeing them, understanding them, writing them, visualizing them? It sets the stage for a lot of later goals with students. So in class, we actually did begin slightly last Wednesday, and I began by having you write a word problem that you thought was appropriate for a first grade student. And most of you wrote some very basic problems. For example, Adam had 3 cups of coffee in the morning and 4 cups of coffee in the afternoon. How many cups of coffee did he drink? And a lot of the structures are very simple like that. Give 2 numbers, what's the total? And then I showed you these problems, these 4. And had you take some Unifix cubes and try and solve these as if you didn't know the answer using only visuals. And if you recall, you noticed 2 things. Number one, the structure of these were actually more complicated than most of the problems you all wrote. These didn't just give 2 numbers to add or subtract. It had the unknowns in various positions. Sometimes we didn't even know the starting number. So the structures were a little bit more complicated. Also, we noticed that, again, you don't have to have a lot of computational skills to solve these. We can use the blocks to act them out, to visualize it, to make stacks, to use colors, and that's a good focus here. Just focusing on a visual way of making sense of the word problems, not just trying to jump right to the answer, but acting it out, seeing what it looks like, getting the good strategies there. So these word problems basically represent what we see in the Common Core standards in first grade. If we look at the first grade standard here that's bolded, Operations and Algebraic Thinking is the domain. It says, use addition and subtraction within 20 to solve word problems involving situations of adding to, taking from, putting together, taking apart, and comparing with unknowns in all positions by using objects, drawings, and equations with a symbol for the unknown number to represent the problem. 2 things to notice about this first grade standard. Number one, it sure sounds an awful lot like algebra. Unknowns in all positions, equations, symbols for the unknown. And you've got it. Students are doing algebra across the grades. We just call it algebraic thinking, and it's age-appropriate algebra is what it is. Second thing, it kind of talks about situations, and there's 4 of them. Adding to, taking from, putting together, taking apart, and comparing. And actually, there's 5 the way listed here. But these are called the structures of addition and subtraction. And this is what Van de Waal is going to unpack in Chapter 8 with us in the beginning, is really this standard. And so that's our goal, is let's make sense of this and get a deeper understanding of some of this early jumping into addition and subtraction structures. So on your note sheet, for the first thing that we're jumping into, on number 2 on that first page, a bit note on vocabulary. In Chapter 8, Van de Waal talks about semantic equations. So what does that actually mean? These are equations where the numbers are listed in the order that most closely follows the written problem. Well, let's take a look at an example. Here's a word problem. Rose has some starbursts. Her friend Joshua gave her 6 more. Now Rose has 14 starbursts. How many starbursts did Rose start with? So there's many ways to write an equation for this, actually. There's many ways that could get the answer or to kind of represent how to find the answer. But a semantic equation is the one that most closely follows the way this problem is worded. It's helpful because it's a parallel structure to the wording of the problem. It might look like this. Rose has some starbursts. That's an unknown. So as you can see, my equation starts with an unknown line, or a question mark, or a box, some symbol. Then it says her friend Joshua gave her 6 more. Okay, so we see the plus 6 for that 6 Joshua gave her. Now, Rose has 14 starbursts. So that's the equal 14. And now we can try and solve for how many starbursts did Rose start with. That was our initial unknown. So the semantic equation is just a parallel structure to the wording, and it's a helpful tool to help students see the connection between the story and the algebraic equation there. So we're going to be writing some semantic equations, so we will come back to that. All right, we're going to start with addition and subtraction today. So let's jump into these two. Van de Waal breaks this down into 4 structures that any word problem could be labeled as one of these 4 structures, and kids are expected in first grade to get experience with all 4 structures. So let's break this apart, and on your note sheet we're going to start, this is section 3, with the join structure. The language here is a bit different than Common Core, but they're meaning the same thing. You'll see the parallel. So in join, there's a structure. You have 3 things, 3 numbers you're looking for, or the 2 typically you have and 1 you're looking for. There's an initial amount, right? And then some change is happening, which leads to a result. It's action-based. We're physically combining 2 amounts. Again, like Adam had 3 cups of coffee in the morning, then he got 4 more in the afternoon. How many does he have now? We see that there. And this is children's informal view of addition. It's kind of where typically things start, and most of the word problems you wrote followed this model. They were probably a join structure. But the unknown can be in any position. Let's take a look at an example. So, for example, if we say Chloe has 2 toys and Kingsley brings her 3 more, how many toys does Chloe have? Well, in this case, we have the initial amount, the change is 3 more, and we don't know the result. So this would be called a join problem with an unknown result, or join missing result problem. But we could put the unknown in any position. For example, what if we did this one? Chloe has 2 toys and Kingsley brings her some more. Now she has 5 toys. How many toys did Kingsley bring her? In this structure, we see the initial amount is 2, the change is actually the unknown, and the result is 5. So we'd call this a join structure with an unknown change, or join, missing change structure here. So with that, on your worksheet, basically, this is the second page of your worksheet, there are 3 problems about James and marbles here. What I want you to do in a second is to pause the video and to write down what you think is the correct structure for those 3. For example, you might say, this is a join missing initial, or a join missing change, or a join missing result problem. It's going to be one of those 3. And then to write what you think would be the semantic equation next to it. So I want you to do that now. Press pause on the video. Take a couple minutes, just write down what you thought, and then I'll show you the answers. Okay, press pause. All right, now that you've thought about it, here are the answers. Again, you can pause to check your own and do corrections, but we can see here the correct answers for those problems. So double check your sheet, and if you have any to correct, just go ahead and correct it and think about why there's a difference between yours and this one. Okay? All right, well, let's keep going on. The next structure on your note sheet is called the separate structure. Van de Waal, I think, calls it taking apart, same as separate. This one is just a little different because it's really the basic view of subtraction. We have an initial amount, and there's a physical action of taking something away. So we are removing something from the initial amount. Adam had 4 donuts in the morning. His son ate 3 of them. How many does he have left now? So it's just instead of adding something in, we're physically taking something away. And this typically is the most basic structure for subtraction problems. And again, the unknown can be in any position. So, for example, Chloe had some tennis balls. Kingsley stole 2. Now Chloe has 6 tennis balls. How many tennis balls did Chloe have to begin with? Well, here we see the unknown here is the initial amount. So we would call this a separate structure with an unknown initial amount. Yeah, makes sense. So that's where the unknown would be, in that initial amount box. And if we wrote a semantic equation, it would be like a box, -2 equals 6. That would match the wording there. So again, on your note sheet, here's 3 new problems about Victor and Skittles. What I want you to do is, in a second, same thing, is to press pause. And on your worksheet, I want you to go ahead and first, do what you think is right. These are all separate structures, but is it an unknown initial, unknown result, or unknown change? And then write down what you would think is the best semantic equation that models the structure. Okay, so go ahead and press pause now. Okay, now that you have taken your first stab at it, here are the answers. So like before, go ahead and check to see if you had the same answers and the same semantic equations. And if not, go ahead and do some corrections and think about the differences that may exist between the two. All right, let's go on to our third of the 4 structures for addition and subtraction. And this is our part-part-whole structure. And we talked about this in class with number sense as well. This is a little different. The reason this is different is there's not a physical action. We are not adding something in, like join, and we are not removing something like separate. We basically have 2 parts that are already here, and we're just putting them together. And that's the big difference. No physical change, just putting together like what we already have. And the picture here is a different picture. It just shows, 2 parts are going to make the whole. So let's take a look at an example. So Chloe has 2 types of squeaky toys, birds and alligators. She has 9 toys in all. If 5 of the toys are squeaky alligators, how many bird toys does she have? Well, when you read that, you'll notice that she didn't get more toys. No one took away toys. She just has 9 toys. And some are alligators and some are birds. That's why this is called the part-part-whole structure. Nothing is being removed or taken away. In this case, if you think of what we have, is we have the whole, we have the 9, and we have one of the parts, we have the 5, but we don't have the other parts for the birds. So this would be called a part-part-whole structure with a missing part. All right? And if you did a semantic equation for this one, since the 9 comes first, I might say 9 equals 5 plus question mark to try and closely match the equation to the wording. Now, I will say that the semantic equation, sometimes there are more than one right way to do it. And on some of the examples coming up, I'm not going to be legalistic. There could be a couple right ways to interpret it. You just want to have the numbers follow in the order they come in the problem as best you can and have it align with that. So again, this was called a part-part-whole structure with an unknown part. Okay, well now you're getting the routine here. So on your worksheet, now we have 3 problems about flowers and pictures, I think, there. So in a moment, press pause, and you're going to label the structure first. These are all part-part-whole, but are they unknown part or unknown whole problems? And then write down what you think would be a good semantic equation. Okay? So go ahead and press pause now. Okay, now that you've tried it, let's take a look at some possible answers. So here are some possible answers. Take a look and see if you got the same as me. If not, go ahead and correct it. And again, you might be able to argue some different semantic equations, so there may be some leeway there. All right, once you have that checked, let's go to the fourth structure and last structure for us for addition and subtraction, and that is called a comparison structure. So a comparison structure is exactly that. We are comparing 2 quantities. For example, Adam drank 8 cups of coffee. His wife, Kirsten, drank 9 cups of coffee. How many more cups of coffee did Adam drink? So we're comparing 2 groups. And Adam had the larger set of coffee there. Oh no, my wife did, I think. I think I said she had 9, and I had 7. Those are the 2 sets. And the difference is the 2 cups of coffee difference. The key thing here is the difference doesn't actually exist. Like, no one had 2 cups of coffee. That was just the difference between my wife's coffee and mine. And here we see the comparison structure. So let's take a look at another example. Colin had 5 books. Shania had 3 more books than Colin. how many books did Shania have? If we look at this, so Colin had 5 books. Shania had 3 more books than Colin. So Shania doesn't have 3 books. She has 3 more than Colin. So in this case, Shania is the larger set, and we actually don't know how much she has. Colin, it represents the small set, and the 3 is actually the difference. So in this case, this is a comparison structure word problem with an unknown larger set, since we don't know Shania's amount. So this would be what it looks like. The question mark is the larger set, and the small set is 5, and the difference is 3. Now for these, I will say comparison problems and semantic equations. This is where this structure, there can be many right ways to do it. Like in this case, you might say, well, could we do 5, and then Shania had 3 more, so like 5 and then plus 3 equals unknown? And the answer could be yes. Yes, that would be fine to do that way. And you could argue some other ones as well. But let's take a look. Let's just see if you can think through with that one example. This is the last structure page on the bottom of note packet 3. So now we have some comic book problems. Same thing. These are all comparison problems, but these take a little more thought. What's the unknown? Is it the unknown large set, unknown smaller set, or the unknown difference? And then play with the semantic equation and write one that makes sense to you. Again, there definitely could be more than one here. Go ahead and press pause. All right, now that you've tried it, and let's take a look at some possible answers. So here are some answers on the board. Again, think about what you have, think about mine, see if they match, pause if needed, and then let's keep moving on. All right, so those are the 4 structures of addition and subtraction. And a big idea here is that in first grade, kids are exposed to all those types, in a progression over the course of the year, and have to learn to think about them, to visualize them, to really think carefully about what the problems are asking. And as a teacher, it's important to know the differences of what children are being asked to do. Now you may notice in all of those, we're dealing with equations, like the equal sign. Well, that's an important symbol in and of itself. So I want to give a quick nod to that, and we may do more in class, but the equal sign is a very important symbol, and one that's, that a lot of kids have a misconception about. Because sometimes they're given worksheets throughout their career where they always see a number plus a number equals something, or a number times a number equals something. And the kids kind of learn that they think that there's always an answer that goes after the equal sign. Like the equal sign does something, and you put the answer after it. But that's not what the equal sign means. Like if you look at the example on the bottom, 4 plus 5 equals blank plus 2. You can imagine when you give this question to kids, a lot of them write 9 in the blank because they've been wrongly kind of conditioned to think that they have to put an answer after the equal sign. Well, that's not correct. We know that in that problem on the screen, it's not an answer goes there. We have to think about the equal sign being like a balance, right? That the left side has to be the same amount as the right side. So we need to think about more like, well, the left side is 4 plus 5, that's 9. But I don't put 9 in the blank. I need to think about the right side. That also has to equal 9. So something plus 2 has to equal 9. And of course, that correct answer would be 7. So in thinking about this, it's important to note, so the common misconception for the equal sign is to mean like the answer is, kids think that every time you see an equal sign, you have to put an answer. Not correct way to think about the equal sign. So like down below, we just talked about it, but like if you look at these, it says which problem helps promote the misconception and which challenge it. It's just interesting to think like A actually helps challenge, is a good for the kids, right? It's good to see problems where the equal sign isn't always at the end. We want to do that, to think the left side is 7, what makes the right side 7? And B is a good question, right? To look at thinking about the left side and the right side. C is interesting because they don't have to do anything. So it just conceptually, what does the equal sign mean? Is the left side the same as the right side? And there's nothing wrong with D. D is fine to ask a question, but if all of your questions are like D, you can see how kids might get a wrong idea if that's the only way they're seeing it. So Vanderwall offers some quick suggestions. Language is important. He suggests using language about is the same as, is the same number as, is the same amount as, and stressing the precise language of equals. He says research tells us that makes can be a problem, like 2 plus 3 makes 5. It's better to say 2 plus 3 equals 5, just in the sense that makes can sometimes have kids think that an equal sign does something when it doesn't. In the chapter, he talks about seeing visuals, where kids see that left side and the right side can be the same, with pictures, visuals, scales. So just, again, a lot of ways to think about it. More on that later. All right, doing great. Keep up the good work. So we're through the addition and subtraction structures, but let's talk about multiplication and division a bit, okay? So let's talk about these two. So right now, think about this for a second. How many ways can you make sense of 5 times 3? So what does that mean to you, 5 times 3? In class, I would have had you gone to the board as a group and brainstorm all the ways that you can see, think of, and visualize 5 times 3, and there's actually quite a few ways if we stop to think about it. So let's think about it. First of all, there is a correct kind of wording. It's kind of a standard wording in the U.S. of 5 times 3. And semantically, like if we see 5 times 3, it actually does mean 5 groups of 3, which is a different picture than 3 groups of 5. They both give us 15, and they're both correct, but to have the same language, it's important to note that textbooks in the U.S. kind of agree to follow the standard meaning of the first number is the number of groups, the second number is the size of groups, and the last number is the amount. So 5 groups of 3, 5 times 3. If it was 3 times 5, we think of it as 3 groups of 5, which again is a different picture and looks different. Interesting note, there are some other countries that their standard meaning is the opposite. It is switched. So it's purely a kind of a choice that was made. And just to think about how textbooks are doing, it's good for us to be consistent. So let's look at the structures. We're going to look at a couple structures. Again, 4 quick structures for multiplication, but do it a little quicker than addition and subtraction. And the first structure is the main one we start with, and that is equal groups. And equal groups, we're just joining a number of equal groups, right? And as we said, there's a language. 5 times 3 is 5 groups of 3. So for example, the pet store had 5 bird cages with 3 birds in each cage. How many total birds do they have? Makes sense. If you look at the pictures, the first fish up there, that would be a visual picture of 2 times 4. That's 2 groups of 4. And the one to the right with all the tiles, there are 3 groups, with 6 tiles. So that would be 3 times 6. 3 groups of 6 is 18. So that's equal groups, and that's where we start. That's a good conceptual meaning. But another visual that's very helpful for multiplication are array models or area models. Array models always involve rows and columns, right? And when we find area, we always use square units, which is still rows and columns, but it's just a specific way we do it using rectangles and squares. So, if you look at the visuals here, the dogs up there, that's 2 rows of 3. Or the flowers, we see 5 rows of 2. The fishes are 4 rows of 3. So again, it's very similar. It is 4 groups of 3, but the visual is just rows and columns and often called an array model. The area model is just specific to rectangles. So, the difference is just an area model is always a rectangle, always square units, and we see that there. So that's a good visual, that kids often also use when they're learning about multiplication and groups. So the other one here are ones that are introduced after. So if we look at, a comparison structure for multiplication, in this one we are determining the size of a set given the size of another set and how many times larger the unknown is. So for example, if you look at the picture, it says John has 3 times as many apples as Sally. How many apples does John have? I guess if Sally has 2 apples. And so here we see a visual, again a comparison. We see the nice bar models we learned before, again a flexible problem-solving structure, but we can visually see, again, the notion that John has 3 times as much. His groups, he has 3 groups, Sally only has 1. It's the wording here that's important. It always has something about 3 times as many, 2 times as much. So like in the bottom, for her birthday, Gloriana received $5. Her older brother received 3 times as much for his birthday. How much did her brother receive? This would be called the comparison structure, given the language. And then lastly, again, at the upper elementary, early middle school grades, we see the combination structure. And you probably recognize these kinds of problems about finding all the ways of combining all of the items of one type with all of the items of another type. And, for example, Gary's Sandwich Shop has 5 types of meat to choose from and 3 types of cheese. You get to choose one of each. How many different sandwiches are possible? And there's different ways to draw this and visualize it. And so the pictures on the page show some different examples, but often we see tree diagrams or acting out the problem or drawing all the sandwiches. But it's just a different structure, right? This is not equal groups. It's not comparison. It's just called the combination problem, and it's just another structure. For the note, these are the 4 main structures. There are some people that would say there are a couple more structures, but these are the 4 that we just are going to think about as we just talk about multiplication. So with multiplication, like I said, equal groups and arrays are typically where the younger kids start, 2nd, 3rd grade, or really focus on those meanings. And then as you continue to grow, expand on your knowledge, you get to comparison, combinations, and area, and rate, which is a special case. But yeah, it was just a nice note there of progression. So, we're going to spend more time in class on this, but on your note sheet, number 12 says teaching meanings of multiplication. And, just like we say in class, how do you introduce multiplication? Well, with models and context, and relate to prior knowledge, relate to repeated addition, right? Things that already make sense to kids. And we just connect to multiplication as the need arises. So, imagine this activity, just partner 1 rolls the dice, and that dice tells us how many pizza crusts we have. So partner 1 rolls a 6, and so we draw 6 circles. Partner 2 rolls his or her dice, and they roll a 3, and you get, 3 pepperonis on each pizza. So they draw 3 circles on each of the 6, and then they can realize how much pepperoni would that be, and they can count it up and get 18. And we can start here, realizing that, again, just language. We have 6 pizzas with 3 pepperonis on each, gave us 18, 18 things. This is 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, right? And that repeated addition, we can then introduce ideas of a quicker way to do this is to use the notation 6 times 3. 6 pizzas with 3 pepperonis equals 18. And just through activities and visuals and connections, we can look at that. So yeah, we connect to symbols when the need arises. And we'll look at this in class more, but this is just what I was saying. Just, focus on stories, visuals, repeated addition, and build the need for symbols. All right. Really, multiplication, in this case, is just a shorter way of writing a repeated addition problem. All right. So that's a bit on multiplication. Let's talk about division for a bit. A few interesting things about division. So with division, when kids first start with division, they build on prior knowledge again. And here's an important prior knowledge idea that's important to kids. So here's an example. There are 12 stickers and 4 friends want to share them equally. How many will each get? Well, this is a division problem, right? 12 stickers split amongst 4 friends. I mean, this is 12 divided by 4, but we don't have to say divided by, just sharing, right? I mean, equal sharing. Kids know about sharing from early on. And when you share equally, that is division, right? So we build on the idea of equal sharing with kids. That's a great place to start with division. Sharing amounts equally among certain types of friends or other objects. Now with division, we're going to talk about 2 different types of division. And we're going to start with this first one on the note sheets called partition division. But first, we're going to take a look at something. So I asked you to get 20 things earlier, right? So I want you to pull out 12 of those things right now. So if you have paper clips, grab 12 of them. If you have pennies, grab 12 of them. If you don't, pause, go get 12 of something, come back. What I want you to do is take a minute and pause the video, and I want you to act out each of these 2 things. And you should notice that when you act out these things with your 12 objects, it's different how it works, all right? So I'm going to press pause, act these out, and then unpause when you're done, and pay attention to what was the difference in how you acted it out, okay? Go. Okay, so you saw the difference, right? So the first one, you started with 12 things, and she wanted to have 4 groups. So when you did it, it was like dealing out cards. You took 12 things, and you had to put one at a time to create 4 groups. And then you gave, each group a second item, and then a third, and then you were out. So it was like dealing cards almost, wasn't it? You created 4 groups, and then one at a time did it until you put 3 things in each group. Interesting. The second one was different. The second one, you started with your 12, but you knew there was 4 students in a group. So in this one, you actually grabbed 4 things and put it aside into a group of 4, and then took another 4 and put it aside, and then you had a third group of 4. They were different. And the 2 ways you did that really highlight the differences of our 2 types of division structures. So on your note sheet there's 2 types of division structures. Partition division, also known as equal sharing, where the number of groups is known and the size of each group is unknown. And that was the first problem you just did. There was 12 things. You had to put it into 4 groups, but you didn't know how many were in each group. That's partition division, or equal sharing. The second one is measurement division, also known as repeated subtraction. This was the second one you did. You knew there was 12 things. You knew that you were making groups of 4, but you didn't know how many groups. So in this one, you took 4 out, and then took 4 out again, and then we're left with that last 4. And it's called repeated subtraction because you're just removing 4 and 4 and 4 until you have none left. These are the 2 types of division structures that we learn. We just did this in class. But if you look down below, we just talked about these. So feel free to pause if you wanted to look at it. That's what we just talked about. Okay. All right. So what I want you to try is this. So just to get, this is an important process to get. So now that you have 20 things, I want you to try this again with your 20 things with a cracker context, and just want you to act out problem A and problem B, and I want you to ask yourself these questions. In each problem, what's the number of groups, and what's the size of the groups, and which one is known and which is unknown when you do it. So based on definitions, which of these examples is partition division and which is measurement division? So take a moment, pause the video, act it out, answer the questions, then unpause when you're done. Go. All right, so did you try it out? Well, let's see if you got the same thing that I did. So for A, the total was 20, and the number of groups was 4, but we didn't know the size of the groups. We didn't know how many crackers were in each stack. So we know the number of groups, but not the size of the groups. So that is a partition or fair sharing problem. In the second one, the total was 20, but in this one, we knew the size of the group was 4. We knew that there was 4 crackers in each stack, but we didn't know how many stacks or how many groups. That was the unknown. That's an example of measurement or repeated subtraction division, and those are our 2 structures. Okay? So, just an important difference there. So, this just highlights, again, what we just did, but the wording is important. And on your ACE questions this week, you want to make sure that you're thinking about the wording and making sure you get these 2 types of structures just correct to know the difference. The big idea here is we don't quiz kids on, is this partition or measurement? The big idea as teachers is to realize that we're asking our kids to do different types of division and to realize the strategies vary a bit when we act it out. And you can talk about kids with the different strategies, and as they think about what they're seeing, it gives you a way, too, of helping get language to talk about it and talk about the different types, just different ways of doing division problems. Because both the problems are 20 divided by 4. Both the problems with the crackers are 20 divided by 4. The answer is 5 for both. But yet, when we did the visual and acted out, they were different based on if the unknown was the size of the group or the number of the groups. And those could be our semantic equations. All right, well, I think we're wrapping up here. I think this is our last slide. So some tips here, right? So like before, put problems in a meaningful context they can relate to. Use stories, right? The second one, use pictures and manipulatives to make sense of situations. Visuals, 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 manipulatives. Let's look at it. Let's make sense of it. And the third thing is to avoid a keyword approach. Sometimes teachers want to help their kids by saying, okay, well, here's what you do. If you're reading a word problem and it says total, then you're always going to add. Well, that may be true on the worksheet you're using right now, but that's definitely not true across all of math and in many situations, and key words, pretty much you can always find exceptions. So what we're trying to stress here is for kids to think about the word problem deeply, to think about what they're looking for, to act it out, to draw it out, and to think what makes sense to go through. Again, kids don't memorize all these structures we just talked about. This is more for us as teachers to know what they're being asked to do, to give us a way of thinking about it and learning about it. Okay, and we'll build on that in class. So that's it. So basically we are done with our online class. Make sure that you just have filled out your note sheet, put your name on it, and bring it to class on Wednesday. What you can be doing right now is for ACE, I believe it's ACE 5, which you're working on right now, which is over number sense, and then this stuff is to make sure with your group you're making progress, thinking about it, looking at each other's work. On Wednesday, you'll have time to meet in your group and continue working on it. And ACE 5, I gave an extended due date, till for sure at least till Thursday night instead of Wednesday, since we didn't meet on Monday. And that's what we're doing. So I hope you have a good Monday. I'm actually in Nashville right now, Nashville, Tennessee, if you're doing this on a Monday. So hello from Nashville, and have a good rest of your day. I'll see you Wednesday morning, bright and early. Bye-bye.